So last week before the big field trip, we introduced a new topic called simple harmonic motion. How did we define simple harmonic motion? In other words, what is it really? When we see something, how do we know whether it's simple harmonic motion or not? What's the general kind of everyday definition in the way that we think of simple harmonic motion? Motion that repeats itself. Yes, motion that repeats itself. Now, that's not the true definition, but it's the definition, kind of the working definition that we use. Because in the end, the true definition usually results in motion that repeats itself. The true definition of simple harmonic motion is motion in which the restoring force is proportional to the displacement. In other words, if we think back to our unit 2, we learned Hooke's law, F is equal to K times X. Motion in which the force, the restoring force that pulls it back to its natural position, is related to its displacement. As X gets bigger, F gets bigger. As X gets smaller, F gets smaller. Motion in which the force is proportional to the displacement. That's what results in motion that repeats itself. Now, give me an example of simple harmonic motion taking place. Perfect, easy example is a spring vibrating back and forth, right? As it gets further away from its equilibrium position, the force gets bigger. That causes it to be pulled back and ultimately to go back and forth, motion that repeats itself. Another one, another example that we saw on Friday when we went on our field trip was the pendulum. When the pendulum swings back and forth, back and forth, back and forth, motion that repeats itself. In the context of simple harmonic motion, we looked at two more terms, F and T, period and frequency. Now, we've seen both of these before in the context of circular motion. In the context of simple harmonic motion, the definitions are slightly different. Instead of the number of revolutions per second, frequency would be the number of cycles per second, the number of to and fro, number of back and forth, the number of back and forth motions per second. Period would be the exact opposite. It would be how much time it took for one cycle, or time over the number of cycles. Neither of those equations are on your data sheet. There is one, however, that relates the two together that's on your data sheet. What does it look like? F is equal to what? Ryan, F is equal to what? F is equal to 1 over T. Good. 1 over the period. We square that one off because that one is on our data sheet. We just got to be familiar with the other two that aren't on our data sheet, that's all. All right? Good? All right, we also looked at an equation specifically for the period of a pendulum. 2 pi square root L over G. What did L stand for? Gary, what did L stand for there? The length of the pendulum. Good. Clearly, the length of the pendulum matters in how long it takes the pendulum to swing back and forth. And what units would the length of the pendulum be in, Devin? Good. What does G stand for? Kathleen, what was G? Yeah, acceleration due to gravity, right? And that value is going to be mostly, for the most part, 9.81 meters per second squared. Solve for the period. All right, we want to solve for, let's say, L. That's a bit of a tough one. Solve for L. Let's take the 2 pi over by dividing. T over 2 pi is equal to the square root of L over G. Let's take the square root over by squaring. It becomes T over 2 pi squared equals L over G. Let's take the G up by multiplying. L becomes equal to G times T over 2 pi squared. All right, not so bad. What if you want to solve for G? We'll do the same thing. Get L, and then just divide by T over 2 pi squared. So it becomes L over T over 2 pi, all in brackets squared, is equal to G. Okay, this is the one that appears on your data sheet, but we've got to be able to use these ones as well because we see this fairly often as well. All right. Last thing that we talked about before our field trip was resonance. And there was a new term in there that went along with resonance, resonant frequency. Everything has a natural frequency at which it wants to vibrate. If you hit the desk The desk vibrates at its natural or resonant frequency. If you push a swing set and then let it go, it vibrates back and forth at its natural or its resonant frequency. Okay, if you play the bass, okay, in your speakers in your house and the walls start vibrating, the walls are vibrating at their natural or their resonant frequency. Okay, everything has a natural frequency at which it wants to vibrate. Anybody have an old car? Sometimes you're driving down the road, you reach, say, I don't know, 96 kilometers per hour, and something inside the dash starts shaking and vibrating. But then when you get up to 101, 102, it doesn't do it anymore. Anybody have something like that? Yes? Okay. That's because, it's not because of the speed that you're traveling, rather it's because of the frequency of vibration of your engine at that point. Typically, unless you're on a hill, the engine will vibrate, or the engine will go back and forth at the same frequency for roughly the same speed, okay, each time you're driving. So if the engine is vibrating at this many RPMs, this many revolutions per minute, okay, and that happens to be the natural frequency of whatever it is that's vibrating, then it starts vibrating, right? It starts vibrating. Okay, the natural frequency or the resonant frequency of that part in your car or that part in your dash that's vibrating. Glass. Okay, the opera singer makes a noise, she sings really, really loud if it's really, really high pitch, and the glass starts vibrating at its natural or its resonant frequency. Resonance, on the other hand, is that phenomenon whereby we apply a force at the natural frequency of the object. So it's the opera singer applying a disturbance, okay, her voice, a force, at the natural frequency of the glass. It's you pushing somebody on a swing set at the natural frequency, the resonant frequency of the swing set. It's Tom driving his car, having the engine running at the natural or the resonant frequency of that thing in his dash that's vibrating back and forth. Okay? When we apply a force at the natural frequency, the disturbance grows. The object starts vibrating more and more and more and more. Sometimes just vibrates a lot. Sometimes what happens? It breaks, as we saw with the Tacoma Narrows Bridge video that we watched, I believe, on Wednesday, I guess it was. Is that okay? We talked about one more example, I think, of resonance. We talked about the microwave oven. Water has a natural frequency or resonant frequency that's in the range of 2.45 gigahertz. 2.45 times 10 to the 9 hertz. So what? So what? Well, when you apply a force, or in other words, apply a wave at that frequency against water, it causes the water to start vibrating. The molecules of water start vibrating. Okay, when you have vibrating molecules, what is that? It's heat, right? Thermal energy. So it warms up. And then that thermal energy is conducted to the inside of the food by conduction. So it cooks even the parts that aren't wet, that don't have moisture in it, but it requires moisture to get the process going. Okay? We cook the inside by conduction, we cook the outside by resonance. All right? I want you to have a look at page 347. And the questions that I want you to do are questions 1 to 12. I'm going to give you a few minutes to work on those here right now, just to get a good start on it, but not a great deal of time. You won't have time to finish them up. So let's take 5-ish minutes, get a few of these questions done, and have a little bit less homework tonight, okay? All right, let's move forward here. We just did a little demonstration with a slinky with a piece of masking tape in the middle. Okay, that slinky looks something like this. Piece of masking tape that had some red marker on it right in the middle there. When we sent a wave down from me to from me to Javi, we saw that that particle vibrated perpendicular to the way the wave was traveling. And the vibration of that particle we saw was actually back and forth motion. It was simple harmonic motion. So really what we have when we're talking about waves, wave motion, is really just simple harmonic motion of individual particles that are within that wave. Waves carry energy, that's what they do. But how do they carry that energy? They carry their energy via the simple harmonic motion of the individual particles within that wave. Every single molecule on that slinky, as we sent that wave down from me to Javi, was vibrating perpendicular, back and forth motion, perpendicular to the way the wave was traveling. There was simple harmonic motion of millions of tiny little particles, which resulted, when we look at the big picture, resulted in what we call a transverse wave. Now, we had two types of waves. We showed you the first one, transverse wave. That's a wave in which the particles vibrate perpendicular to the direction of motion of the wave. They vibrate in simple harmonic motion perpendicular to the motion of the wave. A longitudinal wave, we also showed you that one. Okay, longitudinal waves are the waves that usually exist in liquids and gases. For example, a sound wave. Here the particles are vibrating parallel. In both cases, it's simple harmonic motion. But in one case, the particles are going with the wave. In the other case, the particles are going perpendicular or 90 degrees to the wave. The transverse wave might look something like this, with the particles vibrating like this, and the motion of the particles like this, the motion of the wave like this, versus a longitudinal wave that might look something like this, where the wave is going like this, and the particles are vibrating back and forth like this. All right, let's label some things now. What kind of wave do we have at the top here? What kind of wave is it? Transverse or longitudinal? Right, transverse, good. Transverse wave. Okay, the wave is traveling maybe this way. The particle motion is this way, perpendicular to the wave is traveling. Now, there's a few things we want to label here. First one being a crest. A crest is the top of a wave. I grew up in Nova Scotia. When I learned to drive, one of the signs that we had to identify on the learner's test, we don't see that very often out here, these signs, but it's called a blind crest. Okay, we had to identify what the sign blind crest meant. A blind crest occurred on the road when you were driving on a road up a hill, and then you'd go over the lip of this hill, over the top of this hill, but you couldn't see. So in other words, maybe someone would turn out onto the road, but you wouldn't be able to see them. So it was basically saying, be careful, somebody might be turning out onto the road, but you're not going to see them. The crest of the hill was the top of the hill. The crest of a wave is the top of a wave. Versus the trough, which is the bottom of the wave. It's like a feeding trough, right? A pig trough. How many crests do we have on this wave? 2. How many troughs do we have? 2. If we do the wave bigger, then we'd have more crests and more troughs. More tops and more bottoms. Now the wavelength, this one's a little bit confusing because this is a new term for us. Not only a new term, it's a new symbol. The wavelength is the distance over which the wave repeats itself. In other words, it is literally the length of a wave. The distance over which the wave repeats itself is the length of one entire wave. Now, the symbol for wavelength is like an upside down Y. That's a Greek letter called lambda. we've got it labeled from the top of one crest to the top of another crest. We could have also labeled it here. We could have also labeled it from here to here, the distance over which the wave repeats itself. In all of those cases, the wavelength, or lambda, upside down y, would be the same value. Now, the amplitude is the height of a wave. And it's related to the energy. In other words, and it doesn't get rocket scientists to figure this one out. The higher the wave, the bigger the wave, the more energy it carries. Right? You're in a wave pool, and you got this little wave that's coming off of wherever it's produced. You're standing there. Okay, the wave goes right past you. It's all good. You get this massive wave going past you, and what happens? Kind of knocks you over, right? Because the higher the wave, the bigger the wave, the more energy it carries. The amplitude is related to the energy of the wave. Now, we're going to label that. The amplitude can be measured from the equilibrium position to the top of a crest, or it can be measured from the equilibrium position to the bottom of a trough. Where it's not measured is from the top of a crest to the bottom of a trough. That's not the amplitude. Okay, that's wrong. The amplitude is always measured from the equilibrium position to the top or the equilibrium position to the bottom. Now, what about our other kind of wave, our longitudinal wave? This isn't a great diagram of a longitudinal wave. It's the best I could do. A longitudinal wave, you remember from the slinky that I showed you just a few minutes ago when Javi was our trusted volunteer at the other end. We sent down these areas of compressions. We sent down these areas of high density slinky. And then trailing that, right behind it, was this area of lower density where the slinky was stretched a little bit. Okay, this is where we have the slinky that's kind of compressed, and this is where it's kind of stretched. The compressions of the slinky are, we call compressions. Okay, where the medium, whatever it is that carries the wave, is compressed. In other words, you get higher density. The medium is of higher density at that point. The rarefactions, on the other hand, is where the medium is stretched. That's where we get low density. Because the direction of the wave is parallel to the direction of motion of the particles, this happens in liquids and gases, primarily. And an example of this would be sound, as well as all kinds of other waves as well, but the one that we see the most often, or one that we experience the most often, is going to be sound waves. We won't bother labeling the wavelength, although we could. We could label the wavelength from here to here, or from here to here, distance over which the wave repeats itself. The amplitude here would be a little bit tougher, just because of the way the wave looks. It's hard to label. So what do we know about how fast these waves travel? Well, waves travel a very different variety of speeds here. We go from anywhere from really, really slow water waves to really, really fast light waves, 3 times 10 to the 8 meters per second, 1 billion kilometers per hour. But how do we find the speed at which a wave is traveling? Well, the easiest way to find the speed at which a wave is traveling is to find the speed at which anything else travels at a constant speed. Waves travel at a constant speed, so we're allowed to use the equation V is equal to delta D over delta T. Now, the distance over which the wave repeats itself would be the wavelength. So we can replace delta D with wavelength if we want, because the distance over which the wave repeats itself is lambda. The time over which the wave repeats itself would be what? You guys know this. What's the time over which the wave repeats itself? The time for one complete wave. You think you know this, don't you? No, not frequency, but you're real close. The time for one complete wave is the period. So we can say V is equal to D over T. That appears on our data sheet, obviously, and we're allowed to use that for waves. But we're also allowed to use V is equal to lambda over T. Now, it doesn't appear on our data sheet in exactly that form. Jazzy was kind of thinking of frequency here. So let's put in a frequency here. Period is 1 over the frequency. That makes this equation lambda over 1 over F, which is the same thing as saying V is equal to F times lambda. This one appears on our data sheet as well. We call this the universal wave equation. I'm just doing an answer key right now for an old diploma exam in Physics 30. In Physics 30, we talk about electromagnetic radiation, radio waves, microwaves, ultraviolet, X-rays, gamma rays. They're waves. They're not mechanical waves like we're talking about this year, but the mathematical analysis of those waves is the same. Okay, an equation that I literally just used just a minute ago as you were sitting and doing some work, and I was working on that answer key. Okay, one of the questions that I did involved this equation, the universal wave equation. You're allowed to use it for really slow-moving waves, like water waves, or really fast-moving waves, like electromagnetic radiation that travels at 1 billion kilometers per hour. But we're also allowed to use this equation as well. Whatever seems to work, whatever fits your givens the best. Let's take a look at one example for this wave speed thing, and then we'll wrap it up for today. 8.2 on page 409, it says, to generate waves in a stretched spring, you oscillate your hand. Oscillate, right? We said before, oscillate means basically simple harmonic motion, back and forth, back and forth. Oscillatory motion, simple harmonic motion, back and forth motion. At a frequency of 2 hertz, the speed of the wave is 5.4 meters per second. We're looking for the wavelength, the upside down y. We got 2 equations that we're allowed to use here, d over t, and we've got v is equal to f times lambda, the new equation that we just learned, the universal wave equation. Which one do you want to try here? Which one seems to fit these givens the best? They're both valid. Which one seems to fit the best? I don't think it takes a genius to figure this one out, right? It's going to be that second equation, v is equal to f times lambda. Let's rearrange it to solve for lambda. The f goes down by dividing. V is 5.40 meters per second, and f is 2.00 hertz. What's the wavelength? In other words, what's the distance between crest and crest, or between trough and trough? .70 meters. It's a pretty easy question, isn't it? As long as you recognize what you've got for givens there, it's a pretty easy question. All right, here's your homework for tonight. I want you to keep working on those check and reflect questions on page 347, questions 1 to 12. You should be done a fair number of those already, but I also want you to look at the practice problems that go on page 409. These 3 questions.